Hello, my name is Gabriel Concha. I'm with Team 24 and this is our project, the Power Pal. Today we're going to be talking about these topics: globalization, standards consideration, feasibility and risk analysis, the plan of action, the multidisciplinary aspect, budget, personnel, and the end product description. Blackouts are a very serious problem that affect everyone worldwide, be they caused by natural disasters such as hurricanes or earthquakes, or poor infrastructure. Our project, the Power Pal, seeks to alleviate some of the issues that arise from this problem, but in order to do so, we have to reach the largest global market possible. And we can do this by listening to the standards set by the World Trade Organization, the ISO, and the IEEE. In addition, to get an adequate feel for how our product might be received in other cultures, we have an international contact, Amparo Martinez, who studies at the Columbia International University, and she said that it would be a good product to have, that it would be able to help many isolated communities that may have an issue with this, but she did also suggest that we should keep the price of the product in mind, as many of these communities don't have as much money as many others do, so it would be important to keep in mind how much the product would cost. Okay, as mentioned before, the international standards help us lower trade barriers, and these are the ones that my team has decided to follow. The first one is the ISO 16484. It is a guide on how to integrate a system into the control system of a building, along with project phases such as design, engineering, installation, and completion. The second standard is the ISO 17800. It's a guide on how the information exchange between a control system and the end user should look like and how it should take place. And the last one, the IEEE 2030.2, is a definition guide on how many energy storage and power system terms can be simplified in order to be communicated more easily to potential clients or investors in order to give them a better understanding of our product. And now I'm going to pass you on to my next teammate who will talk about the feasibility and risk analysis.
Hi, my name is Joanne Daponte and I will talk about the feasibility analysis and the risk analysis. The feasibility analysis is a critical part on each project development because it lets us know how feasible an idea really is. In our feasibility analysis, we elaborate into different categories that are technical, resources, economic, schedule, cultural, legal, and marketing. We give each category a score, and we also compare each category with one another. This is what we can see on this table. Here, 1 means that the categories have equal value. 3 means that one category is moderately more important than the other one. 5 means that the category is severely more important than the other one, and the things go on like that. Here, after we did this table, we can conclude that for our project, the Power Pal, the technical feasibility has the highest weight on importance, followed up by the research feasibility, and in the third stage, we have the legal feasibility. We move on with the feasibility assessment. In the feasibility assessment, we took up the scores we get at each category and we multiplied it by the weights obtained on the previous table. This gave us the weighted score. When we get the weighted score for each category, we sum it up and we divided that by the sum of the weight. This division will give us the weight average. If the weight average is above 3, it means our project is doable. So our project ended up being highly feasible and highly doable. For the risk assessment, the team brainstormed and we came out using the same categories as the feasibility analysis with several risks. We see that we have technical, resources, economic, schedule, cultural, legal, and marketing risks. We gave these risks different classes depending on how much impact they have on our project and how often they appear. We use all this information to create this risk exposure table. Here we compare how likely a risk is to occur and how much impact does it have. With this table, we can conclude that resources, schedule, technical, and marketing have all at least one risk on the severe category. The team, after this information, we came all together and we found out action plans or ways to react if any of these risks occur. After all of that, we conclude that active monitoring is critical during our development stage. And also the team, as a team, we need to allocate enough time not only for the expected development of the project, but we also need to allocate some time for troubleshooting as necessary. With all this concluded, I'm now going to pass to my teammate Renee, who will talk about our action.
Good afternoon. My name is Renee Arquet, and I will be going over the plan of action. A plan of action is essential for any engineering project because it's where all the organization takes place that allows the project to be finished on schedule and efficiently. So for our plan of action, you can see here we have a statement of work, a work breakdown structure or WBS, a Gantt chart, and a program evaluation review technique or PERT chart. The statement of work is a detailed outline of the project. It goes over the scope, the location, the period of performance, all the deliverables when each thing is due, as well as delegates responsibilities to each team member. So you can see here our scope of work is a system that can reliably provide power to a load by switching between power sources. Our location of work is primarily EPG Controls, which is the sponsor of our project, and the FIU Engineering Center. You can see our period of performance here. And here we have the responsibilities that have been delegated to each team member. So David Pelaez is team leader, Joannette and Daniel are software, and Gabriel and I are mostly hardware. Here is the work breakdown structure, or WBS. It's essentially a chart that maps out and breaks down the project into different phases, and each of those phases is made up of multiple tasks. It allows the team to visualize what needs to be done in order to complete the project. If you can see here, each task is made up of a percentage. It basically shows how much that task contributes to the completion of the project, and these add up to the percentage next to each phase, and these add up to 100%, which will mean the project is completed. This here is the Gantt chart. It establishes a timeline for the project, and it assigns due dates for each phase and task, and it's where each specific task is assigned to a team member. So if you can see on this timeline, we have team members next to each task and phase, and this here is where the due dates are assigned to each task. This here is a PERT chart, which takes some of the data from the Gantt chart as well as the WBS, and it creates a sort of flow chart with the deliverables and the tasks, and it shows in which sequence each task and phase are to be completed, and it tells you what day they're supposed to be completed. So this is our plan of action, and next you'll be seeing Daniel DeMonico. Thank you.
Hello, I'm Daniel DeMonico, and next I'm going to discuss the multidisciplinary aspects of our project. As society continues to advance, being able to work on multidisciplinary teams becomes much more relevant. As engineering students, it's our responsibility to be able to work and communicate within multidisciplinary teams so that we can succeed in our roles as engineers in the future. Next, I'm going to discuss the personnel on our team. Our team consists of 5 electrical engineers, all with different areas of specialization, which is very important for this project because there's a big software and hardware aspect to it, and we're going to have to integrate the two aspects together. First on our team, we have Renee Arquet, whose concentration's in power systems, so he's going to be a hardware lead on our team. Next, we have Joannette Aponte, whose concentrations is in control systems. She's going to be the lead software engineer for our team. Next, we have Daniel DeMonico, whose concentration's in embedded system software. He's also going to be a software lead on our team. Next, we have Gabriel Concha, whose concentration's in power systems. He's also going to be the hardware lead on our team. And lastly, we have David Pelaez, who is the team leader. He's going to be the project engineer for our team and assist in both hardware and software development. Lastly, I'm going to talk about the budget. So we've divided it into 2 different tables. The first table is the price for all the different hardware components that we're going to need, as well as the software tools. And the second table is going to be our hourly wage, the hours that we're projected to work to complete this project, as well as lab fees. So you can see here on our first table we have everything tabulated for the price of breakers, to different wire gauges, and to voltage and temperature sensors. And lastly, we have the budget breakdown by resource, So we have the projected hours that we're planning on working, our price per hour, and the lab fee that we're going to have to pay for it. And all comes down to a grand total of $12,100.
Hi, my name is David Pelaez, and I am presenting on end product description and other deliverables. Here on the screen, we have a level 0 block diagram. This displays a general outlook of the PowerPal and how it operates. As you can see, we have a programmable logic controller. Attached to it, sensors, a human-machine interface, an Ethernet cable, which will provide communication for the PLC and the HMI, 3 sources being utility power, generator power, and solar power, as well as a power supply. Here, we have a level 1 block diagram going further in detail into the operations of the PowerPal. As you can see here, we have a battery which will be sending a signal to the programmable logic controller and human machine interface. We have a voltage sensor that will be receiving the signal from the 3 sources, and the voltage sensor will communicate the readings with the programmable logic controller. The programmable logic controller will be sending signals and commands such as open and close breakers to the relays, as you can see here. Here we have a level 2 battery block diagram. So our battery is going to receive a 120 volts, 50 through 60 hertz AC signal. We're going to step down that voltage, rectify the AC signal, convert it to DC, and filter it to get a smooth DC signal, and then regulate the voltage being 24 volts DC output. Here we have a level 2 programmable logic controller block diagram, and this is looking at the inner workings of the PLC. As you can see, we'll be sending inputs to the central processing unit. The central processing unit will be communicating with the memory, transmitting and receiving signals. A power supply will feed a signal to the central processing unit. We will have a communication device such as the Ethernet cable, TCP/IP, and we will be outputting from the central processing unit. Here is a level 2 HMI block diagram. And as you can see, our HMI will be touchscreen, so the operator will be able to configure and simulate the program. Here we have a table providing further details of like amperage, voltage of each module. So for example, here we have the battery, which will have an input of 120 volts and an output of 24 volts DC, a voltage sensor, which will be sensing 480 volts from the sources, 50 through 60 hertz, and it will output voltage readings, temperature sensor that will be taking the temperature of the enclosure, human machine interface, which we will be inputting a 24 volt signal, also an Ethernet, and we will be outputting on the screen displaying the breaker states, critical values such as voltage and power. The programmable logic controller will have an input of 24 volts DC, and it will be outputting commands such as open and close breakers. Other deliverables that we will be providing to the users will be things such as a user manual, video presentation, and a final report. In conclusion, we have covered globalization, standards considerations, feasibility analysis, risk analysis, plan of action, multidisciplinary aspects, personnel, budget, and end product description. Thank you, guys.